working on the SLOD project, and I'm going to show some of our recent work today looking at sloshing fluid in vertically vibrating systems and the induced damping effects you get from the sloshing fluid. And we'll cover some of our numerical and experimental investigation into this. So I'll start off quickly with just an introduction into the background, and then we'll cover the experimental research that Lucian's done as well. And it kind of gives us a background into what we've been trying to model with SPH. Following on for this, I'll cover SPH formulation and then some of our experimental and numerical results as well, where we're comparing the actual free surface behavior of our modeled fluid against the experimental recordings as well. Okay, so if we imagine there isn't a global pandemic and we're actually getting to go on holiday somewhere nice, and we're flying along in our aircraft and we undergo some turbulence, you look out the window and you'll see your wing shaking as well. And within your wing, that's where your fuel's stored. So as we undergo this turbulence and gust loading, all that fuel inside your wing is also getting is sloshing about, and it's actually absorbing energy and dissipating energy as well, and damping out the motion of the wing. So the objective of this SLOD project is actually to understand and quantify the induced damping effects you get from this sloshing fuel in aircraft wings, and provide validated methods for modeling it and experimental investigation as well. So this is to take into account the actual effects of fuel sloshing in the aircraft design as well. So hopefully we can design lighter wings, more efficient aircraft as we go on. So the objective of the work I'm presenting today is we're looking at fuel sloshing or just liquid sloshing in vertically excited tanks. The idea for this is we want to simplify the structural motion of an aircraft wing. So we're just looking at the main vertical motion of aircraft wing tanks. And to investigate this experimentally, Lucian has designed this rig called the T-beam, and its objective is for a lightly damped linear motion of our tank. So that means we can extract our fluid-induced damping easier than if it was a non-linear system. And to do this, he's had these two steel strips that are joined together in a T shape. And this connection on the left between these two steel strips, which you can see around here, this allows the beam at this connection to move in plane, both in rotation and translation. And this gives us a much larger linear displacement field than if you compare it to a beam which is fixed on both ends. And because we have a nice linear system here, we can then change this just to a single degree of freedom equivalent, which has equivalent mass, damping and stiffness as well. So all the results I'm going to show are at the maximum displacement, and this means our tank's in maximum accelerations of up to 7G in the vertical plane, and it's oscillating at around 10 Hertz. So we'll start off with some just quick experimental results for the background as well. And what we can see here in the plot on the left is we can see our dry tank plotted in grey, and this is the displacement of the dry tank. So it starts off this 14mm condition, and you can see there's very little damping in the dry structure. But when we fill the tank up to 50% of its filling level, we can see in this blue curve there's this initial really strong increased dissipation from the fluid inside. And we fill the tank up to 50% because in some of our previous work we found out that a 50% filling level actually maximizes the amount of dissipation you get in a vertically vibrated system. We actually add mass to the dry case here. This is to keep our mass and our frequency the same between both the dry and the wet cases, so then they're dynamically comparable. But if this is in a linear scale here in our displacement, if we actually look at a logarithmic scale here, so this is a log of the acceleration envelope of our wet and our dry cases, what we can initially see is that our dry structure is very lightly damped here. We're only looking at 0.23 to 0.35% of the critical damping for that structure. But when we fill it, we see these three distinct linear damping regions emerge in the transient response of our structure. Now we have these three regions. We're going to refer to them as R1, R2, and R3, depending on the order they arrive in. And each one has a very distinct flow regime within the fluid inside the tank, and it also has a very distinct damping ratio to go with that. So if we start with R1, this is the initial response to the fluid at these very high accelerations up to 7G. And you can see this presents here a really turbulent fluid motion in this highly complex free surface behavior. Energy is dissipated from the system here from these repeated impacts from the top and bottom surfaces of the tank, that's drawing energy out of the structure and dissipating it within the fluid. And this presents our largest damping ratio for this wet case here. And it also has the maximum, So as we then move on and this motion decays out and it drops below 1G, we move into our second region we call R2. And within R2, what we see here is this mostly symmetric fluid nature here. The free surface is modulating in this symmetric nature. So just like in a kind of a dynamic system, a dynamic mechanism where you have resonant conditions, you also have resonant conditions in your fluid as well. So when you excite a fluid at a certain frequency, it's going to undergo these resonant mode shapes. And this here, what we see is called the first symmetric sloshing mode. And we'll see our free surface should oscillate at half the excitation frequency. So the amount of dissipation is less within this region because the dissipation here is only from driving the fluid within one of its mode shapes. But it still has a relatively large time duration, up to 5 seconds within this R2 region. And here we're looking at this as the main focus of our work as the results I'm going to present as we go on. But as R2 moves on and eventually decays out, we then move into this R3 region. Now, the fluid is mostly stationary here, not much is going on, so our fluid mostly returns to behave like a fixed mass. So we'll see there is no fluid-induced damping here, we mostly return to our structural damping behavior. And just for completeness here, Lucian has developed this technique where we can actually extract the free surface displacement from high-speed camera footage. And he's done this, let me show it here. This is a really good technique actually, and really helpful for our numerical investigation because we have a direct surface displacement we can compare against. And these were just taken from the high-speed setting on his phone, so it's a really handy tool. And we'll be using these later in some of our results to actually compare the SPH surface motion as well. Okay, so moving on from now, looking at our SPH formulation. What we have here is just a single phase weakly compressible framework. Our momentum equation is fairly standard, we're just looking at normal pressure gradients, and we have a laminar viscosity here, so we're not actually resolving any turbulence in the fluid. And that's something we need to look at in the future as well, hopefully. We also include surface tension, which I'll come on to in the next few slides. And we found this surface tension is actually quite important when we're trying to model this R2 motion, this symmetric surface nature. So I'll cover that in a sec. We include delta SPH as well in our continuity. So this is a density diffusion term, which helps smooth out our pressure and our density fields. And it also helps give us a more clear hydrodynamic force acting on the structure that isn't as noisy. And within the delta SPH, we use the corrected formulation here, which has the renormalization matrix present as well. If we didn't include this corrected term, what we would see is diffusion of the free surface particles away. But because obviously we want to track the free surface and we want to apply surface tension to it, it's better to use this corrected delta SPH formulation to ensure we get a clear free surface. Equation of state is fairly standard, but we use new mark integration to actually march in time. And this is just using fixed point iteration and marching the particles forward until they're converged at the next time step. We use a C2 kernel, and we also use dynamic boundary conditions. So to calculate our hydrodynamic force acting on a structure, we essentially take the effective accelerations between the fluid particles and the boundary particles, obviously multiply that by the boundary mass, and then that gives us our hydrodynamic force acting on the structure. So as I mentioned, we found it was quite important to model surface tension as well. And there's two main methods for this. There's the pairwise force and the continuum surface force. So pairwise forces, they're based on the actual causation of surface tension itself, this cohesive force between molecules. But what we've noticed as well is within our formulation, we get a lot of particle disorder, especially when we have these really strong impacts of the fluid against the boundaries. And where we have this particle disorder, it actually causes these pairwise models to induce surface tension-like effects within the internal fluid. And that's not something we want when we're trying to model dissipation effects and the energy dissipation in the fluid, when this internal surface tension behavior isn't really that realistic. So instead we use a continuum surface force. This is where we compute surface normals and calculate the curvatures and then the resulting accelerations from these. So our CSF model, it focuses on robust calculation of these surface normals, these vectors that point out the surface. We need this in the presence of, strong particle disorder because we're not correcting through any particle shifting techniques. So first we calculate the normals and then we correct them through these two steps. And the first step is we times it by the renormalization matrix we previously calculated from delta SPH. And this does some correction for particle disorder. And then we again smooth it with a Shepley interpolant just to try and remove any spurious normals that may arise. Also, in the presence of boundaries, we also prescribe these normals according to our defined contact line dynamics. So you can see these two videos in the right here. In the top, we're looking at the 70-degree contact angle, which is what we expect to see in our experimental work, water acting against an acrylic tank. Whereas in the bottom one, we've got 150 degrees for our contact angle, and this is more representative of a kind of hydrophobic surface. And then from these modified normals, we calculate the surface curvature, and then the resulting surface tension accelerations in this fairly classical Morris formulation. Okay, so that was our SPH formulation, and that solves our fluid. But obviously, we're dealing with this coupled problem where our fluid changes how our structure moves and our structure changes how our fluid moves. So we also have to solve for the structure. And we do this with a partition approach. So we can use any structural representation we want for the structure. And we couple them together through this translation of the kinematic conditions of the structural solver move over to the SPH boundaries, and then the SPH hydrodynamic force acts on our structural solver. And we couple these together through a strong or tight coupling methodology. And this just sub-iterates the solvers until they are converged at the subsequent time step. And this just ensures we are conserving energy in this FSI system by ensuring everything is synchronized. This usually takes 3 iterations for convergence. So this in itself triples our runtime cost straight away. And what our criteria of convergence is that we say our structural position and our hydrodynamic force must be converged between these coupling iterations for us to then move on to the next time step. And this is essentially saying the work done by the fluid on the structure is consistent across our coupling iterations. And because we can use any model, we just use a simple 1 degree of freedom mass spring damper model. This is thanks to Lucian for designing a really good experimental rig that is mostly vertical, so we can just use a 1 degree of freedom oscillator. We have a small nonlinear damping term in here. This is just to account for some nonlinearities in the dry structure, but it's very minor, this. Okay, so now we'll start moving on to some results. And what we see here is just kind of the global response over the, well, here 9 seconds of simulation time, comparing the experimental acceleration envelope against the SPH envelope. And what you can see here in this blue line is the experimental envelope, and in this very thin red one, it's quite, sorry, it's a bit hard to see, we can see our SPH response. And during R1 here, what we can see is there's actually a very good match between the SPH and our experimental induced damping within R1. And that's because in R1, most of the energy is dissipated by these strong impacting scenarios with the top and bottom tank surfaces. So even if we don't get the subtleties of the actual fluid motion correct, we still get a good approximation of the this damping ratio here in R1. And what we've also overlaid here as well is the results for an equivalent mechanical model. And this is us representing the fluid in the tank as just a bouncing ball. So we have a ball that bounces in a tank. And as it impacts the tank, a coefficient of restitution imparts a loss of momentum on the system. And you can see even this very simplistic case of a bouncing ball still got some relatively good approximation of the induced damping effects in R1, because it's mostly a result, as I've been saying, of strong impacting. What we actually find is as we move into R2, which was this first symmetric sloshing mode, here is when our correlation breaks down. And here it's because the subtleties of the fluid motion, the subtleties of the induced damping mechanisms actually have a larger effect and are harder to model in our SPH results. So the focus of our work here is looking at this R2 region because it still has significant duration. Now it's lasting for around 5 seconds here, despite being at a lower damping ratio. It's still an important region of dissipation in the fluid. So just for a datum here, we'll look at the experimental surface response. And what we can see here in the bottom plot is what I call a surface trace. It shows the evolution of the free surface in time. So our x-axis is time starting at this point in R2, and our y-axis is some position along the tank where the color at that position shows us our amplitude. So if we take a slice of some point on this trace, it's showing us the instantaneous surface displacement at that time. And the first thing to notice here is that for the experimental case, this trace is almost perfectly symmetric. Well, this is what we expect to see. This is the first symmetric sloshing mode. So yeah, so in the top plot, what we have as well is the midpoint displacement. We take the midpoint of the surface as a kind of reference position, and we've plotted that in red over our tank displacements. What you can see is that the surface displacements are much larger than the structural displacements in R2. And as the large amplitude surface dies out, we go into R3. And this is what we expect to see. The result of the fluid induced damping in R2 is a result of us driving this large amplitude surface response of the fluid in one of its mode shapes. So as we move from R2 to R3, we get this reduction in our surface amplitude, and obviously our fluid induced damping decreases here from about 0.9 to about 0.2% into R3. So as I've been saying, fluid also has resonant conditions, and because we're exciting the fluid in this particular mode responds at half the excitation frequency. So what we see is the fluid surface responds in this 2-to-1 ratio where it oscillates at half the excitation. And there are other modes you can get present in fluid. They go up in multiples of excitation, but these other modes are less present than this dominating first symmetric mode, which acts at half the frequency. So if we then follow on to the SPH results, these are the ones without surface tension, just starting off. What we can see in the trace in the bottom is we no longer have this symmetric nature of the fluid, and instead we see these yellow streaks up and down on the plot. And these yellow streaks are actually showing us this asymmetric wave that moves left and right across the tank, which we've got a picture of here. So what's happening is we have these slight anti-symmetries in our initial conditions, and these are propagated through R1, that very chaotic fluid motion, and then they become these very strong asymmetries as we then die out into R2. And they take the form of these breaking waves moving across the tank, and these stop us from setting up these perfectly symmetric first symmetric mode. So because we have these breaking waves, we are no longer driving the fluid in one of its resonant conditions. And because we're not in a resonant condition, we do see this reduction in the fluid-induced damping in R2. And we drop down from about 0.9%, which we saw experimentally, to 0.54%, which we see in this SPH run. Additionally, just to provide a kind of metric of, a quantifiable metric of comparison between the SPH and the experimental surfaces, we use something based on the modal assurance criterion. And this is taking the normalized scalar product of the points on the surface, computing that, and it gives us a value between 0 and 1, where 0 shows no correlation and 1 shows good correlation between the surfaces. And what you can see in R2 is this very cyclic nature of this correlation metric. And that's because there isn't much correlation between these two surfaces as we get this longitudinal wave motion. But if we then move forward and turn the surface tension model on, what we now see is our surface trace returns back to this symmetric nature. We can see down here. And this is because these previous asymmetries that were present were taking the form of these highly curved surface features, these breaking waves. And our surface tension model now acts to attenuate these highly curved features. These aren't directly driven by the vertical excitation. So as soon as they're attenuated, they're not present anymore, and we get to retain ourselves in the symmetric sloshing mode. So now again, we're driving the fluid in its first symmetric sloshing mode in its resonant conditions. So we do see an improvement in our damping ratio. We increase our fluid-induced damping here up to 0.64%. But there's still some discrepancy here between the numerical fluid-induced damping and what we see experimentally. And we're still investigating this, but I think there's three main reasons why. The first one, we're dealing with 2D simulations. So we don't include the large front and aft walls of the tank. And these have significant area. These are about 2/3 of the vertical wall area that aren't included in the simulation. And these present an interface where the fluid-free surface is shearing up and down against these walls. And because we're not including that shearing force, we may not resolve that important kind of important forcing that drives this damping behavior. Additionally, what we see as well is this quite large wetting behavior we get on the surface. These droplets are larger than what we see experimentally. It's a bit of an over prediction. So we may get more fluid that's not actually sloshing. We have a reduction in the sloshing mass here, which may also reduce our induced damping in the fluid. And another reason as well, what Lucian has seen experimentally is we don't always get the same damping in R2. The R2 damping, that fluid-induced damping, is very dependent on how we move from R1 into R2, and there's some significant variation in it. So this 0.64% could well fit inside that range of error for R2, and it's pretty good. It's a pretty good result for these simulations. We need to do some further investigation into this to check this range of error as well in our R2 damping. But what we've seen here is with surface tension, it greatly improves our free surface response because we are attenuating those nonlinear braking waves, and it allows us to set up our resonant conditions in our fluid, improving our overall fluid-induced damping. Okay, and just some videos for reference as well. We're dealing with quite long run times here and very small time steps to deal with these strong impacting scenarios in R1. So our resolution is quite coarse. We're only looking at about 15,000 fluid particles here for each case. And on the left, you can see the results without surface tension, and you can see the presence of this longitudinal wave motion, which is breaking down this first symmetric mode from forming and driving the fluid in that mode. Whereas on the right, we can see it's mostly symmetric, and we are getting something that's more like what we see experimentally. This wetting behavior on the surface is quite large, and actually, as I've been looking at high resolutions, we do see more realistic wetting behavior on the surface. That's something that needs looking at as well. Okay, and just to conclude, we had a look at some of our vertically excited sloshing studies. These were aiming to represent the mainly vertical motion of wing tanks and the mainly vertical excitation of fluid inside aircraft wings. We saw 3 distinct damping regions, each had their own very characteristic flow regime and the characteristic fluid-induced damping as well as a result of this. Our results mainly looked at R2 and the free surface response in that. Lucian developed a experimental method for identifying the free surface, which has provided really helpful information on how actual SPH surface responds in contrast to the experimental behavior. We used a single phase SPH model. This was coupled to a structural model for a tight coupling to ensure we conserved energy in that system, and we used a surface tension method as well. What we saw with the surface tension was it helped attenuate these nonlinear surface features and improved our fluid-induced damping. So further work from here is still looking at these experimental and numerical studies. Only recently, I've actually moved the code over to CUDA with adaptive time steps, so we can actually start doing some higher resolution simulations and potentially looking at this 3-dimensional behavior as well and finding out if that has a strong effect on our fluid-induced damping. So additionally as well, Lucian and I are looking at investigating the kind of nonlinear frequency response of fluid motion in vertical sloshing, just because there are so many different mode shapes present and they each have this very strong non-linear presence in the fluid. We have to make sure we correctly resolve the correct frequencies and the correct frequency behavior in our vertical fluid sloshing as well. And then because we hopefully have a nice validated SPH model, we need to start coupling this with more wing-like structures, so potentially aeroelastic models and actual wing structures, something like an A320 or the Airbus's wing of tomorrow, to see how actually fluid responds under a higher fidelity structural model that isn't just vertical, has bending modes, torsional modes, in and out of modes as well, and how the fluid responds to that. So thank you all for your time. I'm happy to invite any questions if we have them. Cheers.